Can you see my screen?
Yes, sir.
Okay. So let me brief what we did in the last lecture. So in the last lecture, we saw like a roadmap for the course, what we are planning to cover. And then in the first lecture, in the second half of the lecture of the previous lecture, we recalled some basic concepts which we have learned in some other course of linear algebra. Basic concepts. So we have seen just briefly, we just saw the definitions quickly. So as I mentioned that there are two ways to study linear algebra. One via matrices and one via linear operators or linear transformations. And these two things are equivalent. Whatever results we have for matrices, an equivalent result we can obtain or we can state for linear transformation, and we can come from the other direction also. Okay, so I will recall one more thing uh, as a from your previous study, and then we can start the norms, vector and matrix norms in today's lecture. So this topic probably MSO students who did a course with me in the last semester, I have not covered norms and vector and matrix norm, and I'm not sure for other MSc students also from the previous year, the second year MSc students. For them also, I'm not sure whether they have done this. Probably they have learned norm and matrix and vector norm from function analysis, but here we'll restrict ourselves to finite dimension case, and we will look at some of the properties. Some MTL 104 students, I mean some MT6 students, they have done MTL 104 with me. For them also it would be like a slight overlapping, but it won't be like too much. So it would be a new thing for most of you. At least we'll do it in a different way, in a more general way. So we'll start norms and vector and matrix norms in today's lecture. But before I start that, let me recall one more thing which I want to like just state briefly. So we know that if we have a linear transformation from a vector space V to W, and if we fix two bases, one for V and one for W, then we can write a matrix representation for that linear transformation, matrix of that linear transformation. So these, what are the entries of this scale, this matrix? These entries are nothing but the coordinates when we write one basis vectors or the basis vectors or the image of the basis vectors of the domain in terms of linear combination of basis vectors of the codomain, right? Now, in particular, now if suppose we work with suppose we are in an inner product space. That means the vector space together with an inner product. Suppose that we have an inner product, and then we suppose we have a linear operator. Inner product space is a vector space, so we can talk about linear operators on inner product space. So if suppose T is a linear operator on an inner product space, let's say V, and if we fix a basis for this inner product space, then we can again talk about matrix of T with respect to this basis. But this time, because of if we choose not only the usual basis, if we choose an orthonormal basis, then then the matrix of T has a particular form. Not a particular form, but the entries of this matrix, we can specifically tell what are these entries in advance. Okay, so what I'm saying is that if suppose we have, so I'm recalling one more thing from the inner product space, that if we have, let's say we have an inner product space V, and if suppose we fix an orthonormal basis for this, let's say E1 to En, this is an orthonormal basis. Okay. Now, if I take any vector V in this vector space, then I can write its matrix representation. So that I can do for any basis. But since this is an orthonormal basis, I can specifically tell what are the entries of this vector. So the first entry would be the inner product of V with E1. The second entry would be inner product of V with E2 and so on. The last entry would be inner product of V with En. So the advantage of this orthonormal basis is that we can explicitly tell what would be the coordinates of a vector when we write this vector in terms of some basis as a linear combination of vectors from the basis. Okay, so using this, if suppose now we have V and W inner product space over, let's say, over the same field, and if we have a linear operator linear transformation from V to W. So if this is a linear transformation from V to W, now if we fix two bases, let's say one for the domain E1 to En, and let's say one for the codomain W is, let's say, F1 to Fn. These are orthonormal bases. Now if we do this, then also we can find the matrix of T with respect to these two bases B and B dash. And not only that, we can explicitly tell in advance without calculation, we can tell explicitly what would be the entries of this matrix. So the ijth entry of this matrix would be this one, T Ej Fi. The inner product of T of Ej with Fi, this would be the ith entry, ijth entry of this matrix. So this is another advantage of seeing matrix representation with respect to orthonormal basis. Okay. Now, if suppose we have orthonormal basis, if suppose we have an inner product, and if we have a linear operator on an inner product, then we can talk about its adjoint. So adjoint is also a linear operator from V to V that satisfies a certain property. Now, using this adjoint, we can define some other operators like, let's say, we can call an operator T as a unitary if, let's say, T star. If T star is the adjoint of T, then T is called unitary if T star T is identity is equal to identity. Similarly, T is normal if T star T is equal to T star. And similarly, we can say T is self-adjoint if T star is equal to T, right? But then, since we know that we also have similar notion of or similar terminology, or we know that similar terms are also defined for matrices. We know what is a unitary matrix, or at least we have heard from our, in some other course, what is a unitary matrix, what is a normal matrix, or what is a self-adjoint matrix. So we have a notion of unitary, normal, and self-adjoint operators in the operator theory, and when we talk about operators from a vector space to another vector space, and there is this terminology for matrices. Now, since we know that there is a relation between the set of all linear operators on a vector space and also set of all matrices of appropriate size. So there is a one-to-one correspondence. So in fact, one can establish a relation, and one can tell that if suppose V is an inner product space and V is an orthonormal basis, then, and suppose that we have an operator T from V to V, it's a linear operator, then this operator T is unitary, normal, or let's say self-adjoint if and only if the matrix of T with respect to this orthonormal basis V is unitary, normal, or self-adjoint. Self-adjoint is also known as Hermitian. So we can talk about properties of unitary, normal, and self-adjoint operators if we know properties of unitary, normal, and self-adjoint matrices. So we can always establish. Okay, one more thing. So these things we will see. So I'm just recalling the results which are important for us, like that gives us some kind of matrix representation. So I'm recalling only those results. There's also, you know that we talk about rank of an operator. Like if suppose T is a linear operator, then what is the rank? Rank is nothing but the dimension of the range space. This is what we know. And similarly, we know that rank of a matrix. So what is rank of a matrix? There are several ways to define rank of a matrix. So let's say rank of A is nothing but the dimension of its column space. And then there are some several equivalent characterization, like rank is nothing but the number of linearly independent rows, number of linearly independent columns, or dimension of the row space. And there are several other equivalent characterization, right? And then we know that if we have any matrix A, then whether you look at the column rank or the row rank, they are same and it is equal to the rank. And if you have a linear operator T, and if you find its matrix of a representation with respect to any basis, then the rank of T as an operator is same as rank of T as a when you look at its matrix representation. All right, so these are some basic things which you already know. There's also I have already talked about the eigenvalue. So if T is a linear operator, then you can look at its matrix representation, and one can show that whatever be the eigenvalues of T, the same set is also an eigenvalues. Same set is also a set of eigenvalues of its matrix representation with respect to any basis. So it's free of basis. Anyway, so these were some basic things which we will require, and I will not be talking about these things which I already did. So these things, if you have anything which you want to recall, you just go to your previous course or from of your notes, then you look at or you read about these concepts. Here our aim is to cover some new topics, some advanced topics. Okay, so let us start today. So we'll start today's lecture. So from here onwards, I will start formally today's lecture. It is norm, norm of vectors and matrices. Okay, so let us define norms for vectors and matrices. Okay, now before I define, let me give some motivation. So let's say when we are in the set of real numbers, we can talk about which number is large and which number is small, right? Now the question is, if suppose we have vectors instead of numbers, if suppose we have vectors, so what might it mean to say that some vectors or let's say some matrices are small or uh, others are large? What is the meaning of that? Or suppose that we want to say under what circumstances might we say that two matrices are close together or they are far apart, right? So these kind of questions, if suppose we want to ask, or suppose let's say we want to ask, um, we know that what would be the or what may be said about the size of matrices which may be thought of as vectors in a higher dimension space. So matrices can be seen as a vector, so in the higher dimension, right? So if matrix is of size m cross n, you can look at this matrix as an element or as a vector of a vector space of dimension mn. So what about the size of this vector? Or if suppose we are in infinite dimension, then what about vectors in infinite dimension? Can we still measure the size of a vector in infinite dimension space? Okay. Or let's say we know already in Euclidean space Rn or Cn, we know there is a notion of measuring the size or the length of a vector. Right? We know how to define the Euclidean length. But are there other useful ways to measure the size of these vectors than the Euclidean length? So one way to answer these questions is to study norms of vectors and also matrices. So these norms, before I define formally, you can think of these norms as a generalization of Euclidean length in R2 or R3, let's say. You know what is the length in R2 or R3? So if I just recall, so let's recall in R2, what is the meaning? If suppose I have a vector x, let's say x1, x2, then what would be the length of x? What do we know? It is nothing but the square root of x1 square plus x2 square, right? So this is also the Euclidean length. Now we say that two vectors x and y are close if the Euclidean length of the difference vector, so this z equal to x minus y, let's say, this length is a small number, then we say that x and y are close. So if you look at carefully, what properties this length function in R2 satisfy? What are the properties satisfied by the Euclidean length in R2 or R3? So similarly, we can define length in R3 also. But what are the properties satisfied by the Euclidean length? So for example, if I want to look at the properties, so the properties satisfied by the Euclidean length in R2, what are the properties? So you know that if you have a vector x, then its length is always greater than equal to 0. It's always non-negative. So length of a vector, we know that it is always greater than equal to 0. Whatever be the vector, it is this. And we know that it is 0, length is 0, if and only if the vector itself is 0. Not only that, this length also satisfy the homogeneity. That means if I multiply vector with a scalar, let's say alpha, then the length of this vector alpha times x is nothing but the modulus of the absolute value of alpha times length of x, right? So similarly, if we have, let's say, two vectors x and y, and if I look at the length of x and y, then it is always less than equal to length of x plus length of y. So that means this length also satisfies triangle inequality. So now suppose if we want to generalize the notion of this length from R2 to any vector space, then we can expect at least that function, whatever function we want to use as a length, or to measure the vector or matrices, whatever, in a vector space, that function should satisfy similar kind of property, because this is what we expect, at least if we want to say that if we want to talk about length, right? But not only that, norms are these norms which I'm going to define, you can think of them as a generalization of this Euclidean length in R2 or R3, but they are also necessary. These norms, these are also necessary for a proper formulation of some notions like power series of matrices. So for example, if suppose I want to write this kind of thing, a to the power k equal to 0 to infinity, where a is a matrix. So in order to define this kind of term, also it is essential to introduce norm. Or let's say if I want to talk about exponential, matrix exponential, so e to the power a, we already know e to the power x, what is x, what is e to the power exponential function when x is a real number, we know this. But if I replace this x by some matrix a, then what is the meaning of this matrix exponential? So to define this kind of terms also, it is essential to introduce this notion of measuring the size of a vector, or in particular size of a matrix. Okay, so let's say before I give the formal definition of norm, let me also tell you one thing, that suppose that let us look at this example here. Um, Suppose that we have a complex number x, and mod of x is less than 1. Okay? Then we know that what is the meaning of 1 upon 1 by x? It is nothing but so what is this? What is the series expansion of 1 upon 1 by x? It is nothing but 1 plus x square and so on. So now, what if I replace x by a matrix A? So the question is, what if I replace x by a matrix A? So that means if I just do this, then 1 upon 1 minus x, this would be I minus A inverse. So this is the appropriate notation for when I want to write it in terms of matrices. And the right hand side would be 1 I plus A square and so on. This would be the form if I simply replace x by A. But then the question is, when is this expression valid? When is it valid? So then the question is, when is it valid? So this is also one of the questions which we want to answer. We will answer these things, but now you can see that why we need to have something to measure the size of a vector or size of a matrix. So we'll answer these questions by defining norms and then looking at the properties of norm. So let me first define vector norm. So I'll define two kind of norms. One is called the vector norm. I'll tell you what is it. And then just to differentiate this vector norm from the matrix norm, uh, from other kind of norm, I will call the other norm as matrix norm. So it is like it satisfies almost all the properties of vector norm, but in addition to that, it satisfies one extra property. But anyway, so we'll use two terms. So let me first define vector norm. Okay, so what is a vector norm? So suppose that we have a vector space. Let V be a vector space over F. F is either R or C. Then a function which I denote. So this is just a notation for function. Okay. Since for norm this is the standard notation, so I'm using this. But instead of this, you can use any F, G, whatever you want to use for function. Whatever notation you want to use, you can use that also. Anyway, so then a function from V to R is called a vector norm. Vector norm if for all vectors u and v in the vector space V and scalar alpha in F, these four properties are satisfied. So these four properties are actually inspired from the properties satisfied by the Euclidean length in R2. So I'll just use these four properties. I will keep in mind these properties that are satisfied by Euclidean length while defining the norm function. So what this function should satisfy? It should satisfy that norm of V, the function value of V should be greater than equal to 0. So it is non-negative, non-negativity. The second property is that the function value is 0 if and only if the vector V itself is 0. So this is called positivity. Okay. Similarly, the third one, if I look at the function value of alpha times V, then it is nothing but absolute value of alpha times function value of V. So this property is called homogeneity. Then the fourth one, the triangle inequality. If you look at the function value of the sum u plus v, and it is always less than equal to this one, and this is called triangle inequality. So if any function from v to r satisfy satisfy these four properties, then that function is called as a vector norm. Okay. Now a function, there are functions which do not satisfy all the properties, all these four properties, but all satisfy only three, except two, except the second property. So then such a function is called a semi-norm, a vector semi-norm. So a function, so I'll write here, function that satisfies the 1, 3 and 4 properties here is called a vector semi-norm. All right. So any function from V to R that satisfies these four properties is called as a vector norm. Now let us look at some examples. So some examples. So if I take, let's say, Fn, the vector space is Fn, and then I know the standard norms, LP norm. So what is this? So I can define LP norm. What are these? Where P is greater than equal to 1 and less than infinity. For this, if I define this function, this is defined by this rule, where x is x1 to xn. So when p is greater than equal to 1 less than infinity, then I define it in this way. And if it is infinity, or p equal to infinity, I define it, it is just the maximum of the absolute values of all these components of xi. Then you can check that these two functions, so this one here and this function, they actually satisfy all these, they are well-defined functions and they satisfy all the four properties of a norm, and therefore they are vector norm on V, on Fn. Okay. So this you can verify. I'm not going to verify. For example, if you just check the first one, the first property, and also the second one, and also the third one. So the first three properties here, they are very easy to check for these functions. If you quickly check this, then you will realize that these three properties are immediate, very immediate. And similarly for this also, you can do this. In fact, the fourth property for this max function here for infinity, this is also very easy to verify, the triangle inequality. The triangle inequality is also not difficult to verify when p equal to 1. Then also it is easy to check. But when p is strictly greater than 1 and less than infinity, then it is not that straightforward. You will have to use one like well-known inequality. It is called Minkowski's inequality in order to prove this. Okay, so this you can explore. I'm not going to spend time here. I'll give this as an exercise. So the exercise is the following. So show that this is a norm. This is a vector norm on Fn. Okay. So when p equal to 1 or infinity, it's easy to check. That you can verify also. And when p is greater than 1 and less than infinity, for that you, so I'm giving you the hint that you use Minkowski. Minkowski's inequality. Okay, to prove triangle inequality. Okay. Other three properties are very easy to verify, but the last property, that is a bit tricky, and but that also follows if you use this Minkowski's inequality. Okay. Anyway, so therefore you can say that on Fn, this function defines vector norm for all p greater than equal to 1 and less than equal to infinity. But how about how about p when p is strictly less than 1? So this also you can verify. So the question is, again, leave this as an exercise, that you can verify that this is not a norm. Similarly, I can define this function when p is greater than 0 but less than 1, strictly less than 1. Still, like, this function is well defined, but it is not a norm. Okay, that you can verify. So this is not a norm, not a vector norm on Fn for p is greater than 0, less than 1. All right. So we have seen, so far we have seen examples like these LP norms we have seen um, on Fn. So we have seen examples of norms, of vector norms on Fn. The Fn's are the simplest space we know. But advantage of having these some non norms is that we can use these norms to define several other norms. Okay, so far we have seen examples of vector norms on Fn, but they can be used to create vector norms on any finite dimensional vector space. For example, the following result, it says that it gives you a way to define norm on any finite dimensional vector space. Not only that, it tells you that if we have a finite dimensional vector space, then you can define infinitely many norms on different norms on that vector space. Okay, in fact, you can also put some constraint on while defining on that norm. So if you suppose you want to say that define a norm, or you want to define a norm such that for a particular value, for a particular vector, the value of that norm should be this, the predefined thing. So depending on that also, you can like choose the basis in certain way that that norm satisfy the desired property. So the next result gives you a way to define norms on an arbitrary vector space, of finite dimensional vector space. So here we will focus only on finite dimensional vector space because we want to talk about matrices. So matrices are finite dimensional. Okay. So this is the result. So suppose that we have a vector space, let's say V. V is a vector space over F, where F is either R or C. Okay, and let's say N be the, so N dimensional vector space, so finite dimension, so N be the dimension. And suppose that B be the uh, B be a basis of V. So this also you fix any basis. Okay. Now this is V is a vector space over F, and suppose that you know some norm on F. So suppose that this is a norm, vector norm. So norm means vector norm. So this is a vector norm on Fn. So n is the dimension. So assume that this is a norm on Fn. This also you know. Then using this norm, you can define a norm on this vector space V. How you can do? Then you can look at this function. Let me denote this function by this subscript b. B is used for the basis, because this norm, this function depends on this basis. So this is a function from V to R, and how it is defined. You take any vector V, then the function value of this is nothing but the norm of matrix of V, when you represent this V as a in terms of basis elements of this V. So then this function, this is a well-defined function, and this is a vector norm on V. Okay. So this is not difficult to check. First of all, you can see that this function is a well-defined thing. because for every vector we know that there is a unique representation in terms of matrix. So you can have this unique coordinate. So this is a well-defined thing. And then the other four properties, in order to say that this is a norm on V, you have to check the four properties. So these four properties also you can easily verify using the properties, using the fact that the right hand side here is a norm on Fn, and then you know some manipulation in when you have like two vectors, then what would be the relation relation between the matrix representation of two vectors, the sum of two vectors and their individual sums, and this kind of thing you can use in order to prove this. Okay, so this also I leave as an exercise. But the advantage of this result is that it gives you a way to define other norms also. Okay, it gives, in fact, now you can see, or you can say from these, because we know that if V is an vector space over R or C, then there are infinitely many bases. If it is a non-zero vector space, there are infinitely many bases, and for every basis you can define a norm in this way. And there are infinitely many norms for Fn also, we already know, right? These LP norms. So for every basis you can define, let's say, infinitely many norms. Or if you fix a norm here, then if you choose different bases here also, then also you can define several type of norms. Okay. So let us talk about, so we have defined norms, we have seen some examples also, and now we also know a way to define norms. So the proof is an exercise for you. So then the next thing is, okay, let us look at the algebraic properties of vector norms. Like if suppose I have two norms, so I know that now on a vector space I can define like infinitely many norms, different norms. So then the next question is, if okay, if I have two norms, then can we say that the sum is again a norm, or the difference is again a norm? We can ask any question, right? The difficult thing is to answer them, but the questions we can raise. Then what is when the whether the maximum of two, so we, because norms are function, norm is a function, right? So if we have two norm, that means we have two functions. So then we can define maximum of two function. Similarly, we can define minimum of two functions. So the question is whether these functions are again a norm, they also define a norm. Now to answer this, I will state one result first. This proving this result is again is not difficult. It's just you have to use the basic properties of norm, and that's why I will skip the proof. For so far, whatever proofs I have skipped, for them the proof is very straightforward. That means very elementary, using the just the properties of norm. So I don't want to spend time on that. In the next result also I'll just state, but the beauty of this result is that it answers many things, like sum of two norms is again a norm, maximum of two norm is again a norm. This kind of questions it will answer. Okay? And I will define it in a general way. So let us look at the algebraic properties of norm. Vector norms. Okay? So first state the result, and then we will understand what this result says. So suppose that, so let alpha 1, this is a different norm, and so on. Let's say these are m norms. So this is just a notation to denote different type of norms. So suppose these are m number of norms. So let these be m vector norms on a vector space V over F, where F is either R or C. Okay? And let us suppose we have this norm. This is a vector norm on, let's say, Rn. Okay, such that this norm subscript B, this norm satisfies a monotonicity. So what is that? So says that uh, just a minute. Hello, can you hear me?
Yes, sir.
Okay, yeah.
Yes, sir.
Okay. So so let this be a norm. This be a vector norm on Rn such that it satisfies the following monotonicity, that norm of y is less than equal to norm of y plus j with respect to this norm B defined on Rn for all y and z in Rn with non-negative entries. So if the entries of y and z are non-negative, then they should satisfy this property. So the norm should satisfy this property, okay, for all yz with non-negative entries. With non-negative entries. Then, then, if this is the case, if this is the hypothesis, then this new function from V to R defined by the following. If I take any x in V, then the function value would be this one. You take the vector, the vector of m length, of length m, where the entries are nothing but the first entry is the alpha 1 norm of x, then the second entry is alpha 2 norm of x, and so on. The mth entry is alpha m norm of x. Take it, so this is just a vector, this is a column vector, and then take its beta norm. This function is a vector norm. Okay, so let us understand what it says. So although this statement looks like lengthy, but it is very easy. So what it says is, suppose that you have any m norms on V, any norm. So let us call them, let's say alpha 1 norm, alpha 2 norm, and so on, alpha m norm. So these are m norms on V. And suppose that we have one norm, one particular norm, which I am denoting by this beta norm, on Rn. Okay, on Rn. Such that this norm satisfy this monotonicity. That means if I take any two vectors y and z with non-negative entries, then this norm should satisfy this property. If this is the case, then this function from V to R, this defines a norm on V. And how this function is defined? It is defined like you construct a uh, length m vector where the first entry is the alpha 1 norm of x, second entry is alpha 2 norm of x, and so on. And then it is of length m vector in R. And now since you have a norm on Rm and you have a mth length m vector in Rm, so you can find out this beta norm of this vector. So this is how this function is defined. You can verify that this function is a well-defined function. Not only that, this function defines a vector norm on V. So now this result gives you a different way of, or let's say one more way to define norms on a vector space. So we already know how to define like a new norm from some non-norms from the previous result, and now this result gives us another way to define norm. Now the proof is again, proof is not difficult. You just have to use the basic definition of norm, how to prove some function is a norm, that you have to use. But while using that, you also need to use the fact that these are norms on V, and this is also a norm on Rn. So these properties you have to use, but then you can prove this. Now this result is very useful because now as a corollary of this result, uh, so let me ask you this. So first let me write that proof is an exercise for you. So as a corollary of this result, you can see that now you will tell me how to use this result in order to prove the following. So the sum of two norms on a vector space, on a finite dimension vector space, is, because we are talking about finite dimension also only, so I don't have to write this again and again. So I'll just write vector space. Okay, sum of two norms on a vector space is also a norm, also a vector norm. Sum of two vector norms on a vector space is also a vector norm. Now you quickly tell me justification for this, why this is. You can use this result, the previous result, in order to prove this. You tell me how to use this result. And let me tell you that all the LP norms on RM satisfy this. Yeah, all the, yeah, let me just make a comment before that, before you give any justification. So this property, although this looks like very odd here, but all the LP norms on Fn, they satisfy this property. In fact, not only that, so any norm, basically any norm on Rm that is a function only of the absolute values of the entries of X has this property. So for example, these LP norms, if you go back to the definition of LP norm, they are defined by using the absolute values of the entries of X, right? So any norm that is defined by using the absolute values of the entries of X, they have this property. Okay, so this is like not a very strong assumption. I mean, there are many norms, useful norms that satisfy this property. Okay, now you tell me with this information, tell me. So now suppose we have two norms. So let me denote these two norms. Let's say first one is alpha 1 and the second one is alpha 2. So we are given these two norms. The question is how to show that this is also a norm. So this is the question. Now what is your answer? Can you tell me how to use this result?
Take like beta norm to be just L1 norm.
Yes, you just take this beta norm as a L1 norm on Rn on R2 and then it will be fine. Right? So this is very easy to check. So you just take as this beta norm as L1 norm. So this is L1 norm on R2. And then because of the previous result, this is true. Similarly, not only this, you can show that maximum of, so if suppose again we have these two norms, alpha 1 and alpha 2, then you can define a new function which is like maximum of, so the new function would be this one. Norm of X is maximum of norm of X alpha 1 and norm of X alpha 2. This is also a norm. That also you can, this also you can prove using the previous result. Now how to prove this one? What should be our beta norm here? So what is the justification for this?
So this time we take sup norm.
Yeah, you take the max norm. Yeah, sup norm you can take. So this time you take this as the infinity norm, L infinity norm on R2. Okay. Now you, instead of 2, there can be k or any finite number of norms you can take, and then still you can talk about their max. Similarly, you can define the sum of any m norms also. But then the question is, is the difference also. So we have already checked about addition. We have also checked about maximum of two norms, max of two norms. Then the question is, what about the minimum, or what about the difference? Is, is it also a norm? So the question is now, what about minimum of, let's say, two norm? So see, in order to prove the max of these two things, we use the previous result, right? But this only gives us a way to check, but this is not all. Now you cannot use the previous result in order to check whether minimum of two norms is again a norm. For this, I don't know whether it is true or not. You have to give me justification. If it is true, you'll have to give me proof. If it is not, you'll have to give me a counter example. Okay. So this is an exercise for you. Think about it, whether this is true or not. Whether minimum of two norms is a norm or not. The difference of two norm is not a norm. That is not that is not difficult to check. But this one also you need to verify. Either you give me a proof or give me a counter example for this. Okay, all right. Now, as I mentioned again, there are many norms that satisfy this monotonicity. But then there are also norms, some particular kind of norms you can define which do not satisfy this property, and therefore this result is not valid for such norms. For example, I can give you one example here. So if suppose V is, let's say, R2, okay, and then you consider this norm. This is some norm. Let's say I'm just denoting it with this notation. Okay. So what is this? If X is X1, X2, order pair, or you take as a column vector X1, X2, then how to define this? So this is X1 minus X2 plus mod of X2. Now this function, you can verify that this function is a norm. This is a norm on R2. This you can verify. So this function satisfies all the four properties of a vector norm, and therefore this function is a vector norm on R2. Okay. But now so this is a vector norm, but this function does not satisfy this monotonicity. This function does not satisfy this monotonicity of this result here. Why this is not? Because so for example, if you take this matrix or this vector X as 1 0 and Y as 0 1, so now you can see that the entries of X and Y are non-negative. But now if you look at X plus Y, what is X plus Y? So not for this. So let me just first complete the statement here, and then I'll give this example. So uh, if we look at V as R2, and if we define this function subscript V, norm of B norm of X, which is defined in this way here, then this is a norm that is not difficult to check. But now if you look at this function here, this new function X, which I'm defining using the, so whatever will be the conclusion of this statement here. So you can see here this function. So this is one norm, and this is the norm I'm defining here. This function here is not a vector norm. This function is not a vector norm here. So what I'm saying here, I'll give you a justification why this is not a vector norm. But what I'm saying here is that if you, although I have given you examples of norm like these LP norms, they satisfy this monotonicity, but there are examples of norms that do not satisfy this monotonicity. And since if this is not true, then this whatever be the conclusion of this result, that may not be that need not be true. And here is an example. So in the example I gave you one norm, this one. So this norm is not, does not satisfy that monotonicity that you can check. And therefore if you define the function as it was defined in that result, this function need not be a norm, need not be a vector norm. So why this is not true? Because if you calculate, if you take x as, let's say, it does not satisfy the triangle inequality, because if you take x as 1 0 and y as 0 1, then you take the x plus y, calculate this norm here, the function value of this x plus y, this would be 3. And if you calculate uh, norm of x or the function value of x under this function, then it is 1, which is also same as function value of y. So clearly function value of x plus y is greater than the sum of function value of x and y, and therefore it does not satisfy the triangle inequality. So triangle inequality is not satisfied here, and therefore this is not a norm. So this function does not define a norm on R2. Okay, and the reason why this is not defining, why this does not define a norm, because this norm does not satisfy that monotonicity. Okay, this you can verify. All right, so we already have know how to define norms. From new norms from the non norms. So let me give you one more way to define new norms. So that way we will have like various ways to define new norms. I will give you two more ways later on to define new norms. So the next result is again I will just state, but the proof is very elementary again, using the properties of norm. So what this result says, this says that if suppose we have a norm, let's say this is a norm, vector norm. So suppose that this is a vector norm on let's say Cn. Okay, and A be any invertible matrix of size n cross n. So we are given a norm on Cn. Now we know several norms on Cn. There are these LP norms. Then we also know different ways to define norms. So there is a collection of norms we know already on Cn. So take any vector norm on Cn. And suppose that A is any invertible matrix. So there are many invertible matrices. You take any invertible matrix A of size n cross n. Now based on this invertible matrix, you define a function. So then this function, which I am denoting by this one, from the set of n cross n matrices over C R. What is this function? Or not on these, but Cn. Sorry, vector space is Cn here. So from Cn to R, how do you define that? You take any vector x in this, and the function value is nothing but the vector norm of Ax, where Ax is the matrix vector multiplication. For all x in Cn, you define it this. Then this function is a vector norm on Cn. So now again you can see, if you take any vector norm on Cn and if you take any matrix A, then using this result you can define a new norm, right? And why this is a norm? Again, it's not difficult to check. It's very straightforward, using the fact that this is a norm. Yeah. So that way you can check that this function is a vector norm. So the proof follows by definition. Okay, proof follows by definition. So if I ask you a question in the exam, then you don't have to write like follows by definition. You will have to give the proper justification. Okay, so this is just for you. So you verify this and give proper arguments to validate this. All right. So here in the question you can ask me, okay, why this invertible? What if A is not invertible? So the question now, let me ask you, what happens if uh, what happens if A is singular, let's say, that means not invertible. So what would happen if A is, let's say, A is a singular matrix? What can we say about this result then?
Non-zero.
Sir, even if x is non-zero, the ax can be zero.
Yeah, so the first
So the
property,
norm will be zero even if x is zero, non-zero.
yeah, so the positivity is failing here. Okay, all right. So now let me make a comment before I go further. So we have seen so far. So in today's lecture, so far what we did, we have defined vector norm. We saw some motivation, but when then we define formally what is a vector norm on a vector space. And then then we saw some standard examples of LP norm on Fn. But then we saw that using these LP norms, we can define new norms on a given vector space. Not only that, we saw that there are like some these norms satisfies several algebraic properties, like sum of two norms is again a norm, and the maximum of two norms is also a norm. Then we saw one more result here that also gives us a way to define new norm. So far we have seen that there are many different functions. There are many different functions from a vector space to R that satisfy the properties of a norm, right? Or the axioms of a norm. Thus, it is useful. Therefore, it is useful to have many different norms available for us, because in application it may happen that one norm is more convenient or more appropriate than another one for a given purpose. Okay, so if there are several norms, then it is possible that one norm is more convenient and or appropriate than the other one for a particular purpose. For example, as I always mention that if suppose we have different norms. So for example, if suppose we have L2 norm, then the L2 norm has its own advantage. So L2 norm is often convenient to use in optimization problems, because it is continuously differentiable. It is a quadratic, so it is continuously differentiable except at the origin. On the other hand, if suppose we have L1 norm, then L1 norm is differentiable on a smaller set, but it is popular in let's say in statistics, because it provides some like robust estimators than the classical estimators. So L1 norm has its own advantage in statistics. L2 norm is useful in optimization when the quadratic optimization is used, because it is continuously differentiable. Similarly, L infinity norm is the most natural one. L infinity norm, that sup norm, is the most natural one, since it directly monitors element by element convergence, because max norm, what it says, it is the maximum of each element, right? L infinity norm. So it tells us what happens to the entries, to the individual entries. So this is the most like natural one, but unfortunately, analytically and algebraically, it is very awkward to use. So depend on the application, depending on the purpose we are using the norm. one can choose the norm. So it is good to have a like a collection of norms in it. Or in actual application, it happens that the norm, so one can use one norm to develop the whole theory, but actually in application that norm is not useful, some other norm is useful, which is easy to compute, right? So the theory is developed by using some norm, but in practice some other norm is used because the norm which used for the theory is not easy to compute, but the other norm is not useful for the theory, but it is easy to compute for the practical purpose. And therefore it is important to know that what is the relationship between two different norms. You understand what I'm trying to say here? So we have several norms, but these norms are useful for different norms are useful for different purpose. But then we should also have a relationship that tells us, okay, this is how, if I take any two norms, then this is how they are related. In fact, you will see that in finite dimensional case, which we are mostly considering here in this course, every two norms are equivalent. Any two norms are equivalent. So in a finite dimensional vector space, any two norms are equivalent, and this is what I'm going to prove next. So this will tell us that. So when I prove this result will will tell us that, okay, or roughly this result will tell us that any two norms are almost the same. I mean, in theoretical sense, any two norms are almost the same. So for certain purposes, if suppose something is happening for one norm in the vector space, then the same thing would also happen with respect to the other norm. You will see that, for example, convergence in the finite dimension norm space, if a sequence is converging with respect to one particular norm, then it will also converge to any norm because any two norms are equivalent. So for certain purposes, it is this result will be useful, that any two norms are useful, any two norms are equivalent. But in other cases, this result is of limited use, because the way we will prove this, or we will establish this equivalence, that hardly solves the practical purpose. Okay? And therefore still we need to like look at the different norms, or different type of norms, and we need to study the properties of various norms. All right, so with this motivation, we can prove that any two norms on a vector space is any two norms on a vector space are equivalent. Okay, so if you have any doubt, you can ask. So let V be a vector space, and suppose that we have two norms. One I'm denoting by this A norm, and the other one I'm denoting by B norm. Okay, these are two norms, two vector norms on V. Okay, then there exist real numbers the C1 and C2. C1 is greater than 0 and C2 is greater than equal to C1, such that for all x, this inequality is satisfied. C1 times norm x, B norm of x, is less than equal to A norm of x, less than equal to C2 times B norm of. This is true for all. Okay. So when I say that two norms are equivalent, that by that I mean that there exist two scalars, two real numbers C1 and C2, such that this inequality is satisfied for all vectors x. Right? So how to prove this? Let us prove the result. So I will simplify this proof so that it is very easy to understand. So let me first, before I start the proof, let me make an observation here. Suppose that we have a, so this V is a vector space and it's a finite dimension vector space. So let us fix a basis for this. Before I actually prove the this result, let me fix something that would be useful for me in order to prove this. So let us suppose that V1 to Vn, this is a basis, okay, a basis of V. So that means if I take any vector x in V, then I can write this vector x as alpha I Vi equal to 1 to n, where alpha i's are coming from f. So let us assume that f is C. So whatever, so they are coming from f. Okay. Now we can define like this norm. This is an L1 style norm. So L1 like norm. What is this? So I'm defining this function here. If I take any x in V, then this function is defined this way. This is L1 like norm. So what do I mean by that? It is sum of absolute values of alpha i's, the coordinates alpha i's. Okay. Now you can check that this function here, whatever I have defined, the one norm in this V, this is a vector norm. This is because we have already proved this in one of the previous result. This way, this norm is a, so basically what I did here is that I have defined this norm as a this one norm of this one. Okay. Anyway, so this is a vector norm on V. Now I will prove this result that any two norms are equivalent in 4 steps. The first one is that instead of taking A and B, I will show that any norm, any B norm or A norm, whatever norm I take, let's say B norm, I will show that that norm is equivalent to this one norm. So I will in the first step, what I will do here. So I'll complete this proof in 4 steps, and each of these steps is very easy to understand. In fact, very straightforward here. So I will prove this in 4 steps. So the first step, so let me write this here. So we'll prove this in 4 steps for your records. Prove the result in 4 steps. Okay. So the step 1 is that I will show that every norm is equivalent to, or I'm saying that it is sufficient to show that every norm is equivalent to this one norm, the norm which I have defined here. So what I'm saying is that it is sufficient in the step 1. I'm saying that it is sufficient to consider B norm as one norm. Okay. So that means I will show that any A norm or any norm is equivalent to this one norm. Why this is? Because the norm equivalence is transitive. That means if, let's say, if A norm is equivalent to A, because if suppose um, this is the relation we have, and let's say this is the relation we have for some other norm with other scalar C1 dash and C2 dash, then clearly we can utilize this. So assume that here we have this scalar and here we have the scalar satisfy this. So then you can easily, from this you can easily formulate that norm A and norm A dash, these two are equivalent, because from here you can easily conclude that we have this one right? So from here you can say that this and A dash norm, they are equivalent. Okay, and therefore you can say that, okay, even if I prove this result for one norm, that means if I take B norm as one norm, then I'm done, because then because of this fact here, uh, I can prove that any two norms are equivalent. So therefore we will, in the following, we will try to prove this result when B norm is one norm. Okay, not only this, in step 2 also you can observe that how much time do we have. Okay, so in the step 2 I'm saying that it is sufficient to consider only vector x with one norm as is equal to 1. So you take the vectors of which, for which one norm is equal to 1. So one norm is the norm which we have defined here. So if you consider only such vectors, then also we are done. Why this is? Because what we want. So here we want that, what we want that we want C1 and C2 such that this is satisfied, right? So C1, one norm of x is less than equal to one norm of A is less than equal to C2 times one norm of x. Okay, for all x in V and for some C1 C2 satisfying this. This is what we want, right? So if x equal to 0, then it is trivial. It is trivial. This inequality is trivially true. But if x is not equal to 0, then what I can do, I will divide x, since x is non-zero, so I will divide x by its one norm. One norm is the norm, the one norm is the norm which I have defined here. So if I do that, then what I will get? The left hand side I will get only C1, and then I'll get this thing, where what is u? U is x divided by its one norm, right? So clearly from here you can say that one norm of u is equal to 1. But a norm of u I don't know, but one norm of this is 1. So if even if I prove this result for all vectors x such that one norm of x is 1, then I'm done. Then it is equivalent to doing for any vector x, right? So this would be step 2. So in the next step, so in the next two steps, I will show that any norm is equivalent to one norm by proving the result for all vectors u for which for all vectors u of one norm 1, and I will show the existence of C1 and C2 that satisfy this. Right. So let me write step 3 here. Now, in order to show the step 3, I need one analytical property of norm. So what is that? So you can check easily that any norm, let us denote this by a norm, is continuous under one norm. So what is the meaning by that? So what we will show here, we will show that this. So what we will show, so our claim is to show that in this step 3, that this a norm, which is any norm on V, is a continuous function on V under the topology induced by the norm by one norm, induced by one norm. Okay, So how do we show that a function is continuous? We can use epsilon delta definition. So I will show that for any um, so we'll show that to show that for any epsilon greater than 0, there exists delta greater than 0, such that uh, so this is a function. So this norm is a function from V to R. So the absolute value of this minus this is less than epsilon whenever one norm of x minus x dash is less than delta, right? So this is what we have to show in order to say that this norm is continuous under one norm. All right, now you know that because of the triangle inequality of norm, you can verify that since a no, so the given function here, this is a norm on V, right? So this norm satisfies the triangle inequality, and using the triangle inequality, you can show that, or I'll say not that. For any vectors x and x dash, if you look at the absolute of this, the difference of their norm, then this is always less than equal to uh, a norm of x minus x dash. This is by using the triangle inequality. This you can verify using the triangle inequality on this norm. Triangle inequality of this norm. Okay. So now if I take any two vectors x and x dash, so that x and x I can write as a linear combination of basis vectors. Let's say with alpha I, coefficient alpha I, and x dash also I can write as a linear combination of basis vectors with coefficients alpha I dash. Okay, then what would be x minus x dash? This one. So now see, I want to for a fixed epsilon, I want to show that there exists delta such that this is true, right? Now, in order to bound this quantity here, using the triangle inequality, I am trying to bound this quantity here, because then using this, I will eventually bound this one. Okay, so I'm trying to bound this one here. So if I take any x and y, then I know that I can write these vectors as a linear combination of the basis vectors. So a norm of x minus x dash, what would be this? By definition, if you use the definition of no, yeah, if you just use the definition of this x and x dash here, not the definition, this combination here, then what it would be? It would be alpha I minus alpha I dash I equal to 1 to n, right? But then this quantity, now can you tell me how to say that this function here, how to find delta using this information? So we are trying to find delta for a given epsilon. So you can fix an epsilon here. So can you tell me how to do that from here? So what I can say from here, I can say that this quantity is less than equal to, if I replace here with the maximum of Vi, norm of, so this is for entry Vi, right? For a vector Vi. But if I take the a norm, the maximum of a norm of these vectors Vi, and take that common, then this would be less than equal to, you can write it as max of I norm of VIA, and then this would be mod alpha I dash I equal to 1 to n. So what is this? So this quantity is fine. This is just a scalar because the basis vectors are fixed, so this would be a scalar. And what is this one? Can you tell me the next quantity here? What is this? What is this here? This is just one norm of x minus x dash, right? So if I choose delta as 1 upon, or let's say epsilon upon maximum of this quantity here, then I can say, then whenever x minus x dash, one norm of this is less than delta, it will imply from here it will imply that a norm of this thing, or the absolute of difference of a norm of x and x dash, is less than epsilon, and this shows that this a norm is continuous under one norm. Then comes the fourth, which is very straightforward. Now we know that a norm is a continuous function, and if I take the unit sphere, because in that step 2 I have shown that it is sufficient to prove this result for vectors x such that norm of x equal to 1. Now the set of all vectors x whose norm is equal to 1, that forms a compact set. It's a unit sphere, and it forms a compact set. So it is a compact set. Now we have a continuous function here. The norm a is a continuous function, and this unit sphere is a compact set, so it will attain its maximum and minimum. And this minimum I can take as C1, and the maximum I can take as C2, and then I'm done. So what I am saying is the following, that in the last step, step 4, note that this unit sphere u belongs to V such that one norm of u is equal to 1. This is compact in V. And what we have seen here, we have seen that this is a continuous function. This is a continuous function on V under the topology induced by one norm. And this set unit sphere is a compact set. So therefore, by the extremum value theorem, this function will attain its maximum and minimum. So this implies this function attains its maximum and minimum on this set u, such that one norm of u is 1. So therefore we know that the minimum would be, let us call minimum as C1. This is the minimum of a norm of u on the set u such that one norm is 1, and call C2 as the maximum so these C1 and C2 exist. So now clearly, since u is not equal to 0, so any u which is not equal to 0, because u belongs to this sphere, so norm of u is 1. So u is not equal to 0 for all u such that one norm of u is 1. So this implies that this C1 is greater than 0, and of course C2 is the maximum, C1 is the minimum, so C2 is greater than equal to C1. Okay, so what we have is the following, that C1 is less than equal to a norm of u less than equal to C2 for all u with one norm of u is 1. This completes the proof. Okay, so this proof, you might have lost the track, but this proof is not difficult. I tried to simplify it in 4 steps so that you can understand it. So you just go back and look at the notes here, and then you will see that the proof is not difficult. Sometimes it is easy thing is difficult to explain. So it makes things more complicated. So you just go back and look at your notes, and I'm sure that you will easily understand this. Okay, so it's time. I'll stop here. If you have any doubt, you can ask. So is there any doubt? So do you have any doubt? If not, then I will close the meeting.
सर
Okay. Yes, yes, Gopal.
सर नोट्स कहाँ पे करोगे आप शेयर?
मैं नोट्स मूडल पे भी डाल दूंगा, और अदरवाइज इस पे MS टीम्स पे तो मैं डाल ही दूंगा।
ओके सर,
ठीक है, दोनों पे ही डाल दूंगा।
ओके सर, थैंक यू।
Okay. Anything else? Okay, if not, then we stop here, and I'll see you in on Monday in the next class.